All right, in this video I want to finish up some things out of 14.5 that I originally cut out a little bit, but I feel it's necessary. Um, just two quick things here with some examples. The directional derivative and the direction of greatest increase or decrease. I did talk about this one, and it wasn't explained very well in there because I didn't really have like an example. Let's start with directional derivative. It's pretty easy. We're going to be using a dot product. So this is a definition here. I just kind of pre-wrote some stuff here before I started. So if we have a function that's differentiable, then we have that the derivative with respect to v of some function evaluated at some point a, b is going to be the gradient dotted with the vector. So the gradient of f evaluated at the point AB, and we are dotting that, of course, because the gradient is a vector, and the given vector is some vector, of course. Okay. All right, so as our example, we're going to find the rate of change in pressure at a point Q. So here's our point 1, 2, 1 in the direction of 0, 1, 1, where the pressure in millibars is given by the following function, which I have here. But I could not properly write with the program I'm using, so I'm going to write it out. All right, that's a plus yz squared plus x squared z minus xy squared. All right, and then also, just so we know, x, y, and z are given in meters. So the answer that we get is going to be in rate of change is millibars per meter then. All right, so let's go through some steps. So one, let's calculate the gradient of f. All right, so of course we take the partial derivative with respect to x, so to 1,000 gone, there's nothing here, and then with x we have 2xz, and this has an x, so we have minus y squared. Let's see, with respect to y, so nothing here, this is just z squared. This does not have a y, and this is minus 2xy. And then with respect to z, 2yz x squared. Okay. Then we just imagine just plugging in the point we have 1, 2, 1. So this f evaluated, or the gradient of f evaluated at 1, 2, 1. All right, so these are ones. So we have 2 minus 2 squared. Looks like negative 2 here. This is a 1 minus, let's see, a 1 and a 2 there. So it looks like we have a negative 3. And y and z, 4 plus 1. Looks like we have a 5. All right. I think we're okay there. All right, then, now, you could do this abstractly if you wanted actually, if you just at this point, if you wanted to dot it with the given vector and then plug in later. This, of course, is much easier because we just have these numbers to work out. So the directional derivative in the direction of the given v that we have of the gradient, sorry, I've got to put that in there. 1, 2, 1 is just going to be this vector. And then this is just going to give us the rate of change in this specific direction. All right, so we have negative 2 times 0 is 0. Negative 3 plus 1 is negative 3. And 5 times 1 is 5, which gives us a 2. Now, we're not quite ready to answer this yet. The thing that we have to consider is, see how much room I have. Okay, good. So here's what we have to consider. This v that was given was 0, 1, 1. In this direction. That's a 1. Now, consider if we had some other vector, let's call it, call this v1 or something, v2. Well, what if we had a direction vector of 0, 2, 2? Something like that, or some other vector, 0, whatever, 0, a half, a half. So all these vectors are actually in the same direction, but if you were going to dot that to this given vector, I hope you can see without me actually doing it, that we would get a different number. Certainly the negative 3 times 2 would be a negative 6, right? And then the 5 times the 2 would be a 10. And I just said I wasn't going to do it, but basically there's a 4. So notice that this vector is twice as long, and it seems like the direction or the change is going to be twice as great as well. I mean, it would make sense that if you travel twice as far, you're going to change twice as much. So that's basically what's going on there. So we have to consider that if we could make this a unit vector and then dot it to that, it would have given us the actual correct answer right away. However, for this, all we really have to do is, let's just say, and let's just call it a u for, say, unit vector. If we consider that some u here is going to be the vector v that was given, and we divide it away by its magnitude, of course, which would give us the unit vector in that direction. Okay, if we consider that, of course, this is going to be 0, 1, 1 divided by, and the distance here would be root 2. But all we really have to worry about, notice that when we do this dot product, we don't really have a vector here. We have a scalar, a real number. It tells us about a rate of change if we travel in this direction. But if we happen to go root 2 units in that direction. So if we calculate the derivative in the direction of u, where u is this unit vector, Okay, all we really have to worry about is dividing away by this magnitude that we found of the original in the direction of v. Now, direction of v in the direction of this u again is the exact same thing, except this one has been made a unit vector. Because again, we want to talk about rise over run, and we want this thing in millibars per meter, not millibars per root 2 meters, which is further. It's 1.414. So if we multiply by that, that actually gives us that this original 2. So we're really dividing by this root 2 right here, times the 2 that we originally got up here. And our answer is 2 over root 2, which is just root 2. So our final solution here is going to be root 2 millibars per meter, or, since this may be some sort of real life problem, 1.414 millibars per meter. Now, I just took you through that. And again, if you wanted to right away turn this into a unit vector, you could also do that, but then that root 2 would have been in your calculation, and then we involve that later. So it's really up to you. Do you want to make this a unit vector right away? Then you would have that 0, 1, 1 over root 2, and then you would have to dot that to all these numbers, and you would have gotten the correct answer straight up. Or you can just leave it as that vector, but then just remember you have to divide away the length of that vector v you have to make sure it's per unit. You want it per 1 meter. You don't want it per root 2 meters or per 5 meters or something like that. Okay, just a simple example on that. Things don't get too much harder in that area, but okay. All right, now we're still continuing in 4.5, the direction of greatest increase or decrease. Now, what was stated in the other video is basically that the gradient gives you the direction of greatest increase, and then the opposite vector, so negative of the gradient, will give you the greatest direction of greatest decrease. Now, what we just have to worry about is, and this is what I didn't really go through, it's about the direction in the domain, not actually the vector that you get in, say, that the higher dimension, which is, if your domain is 2 dimensions, that's the direction I'm talking about. So if your domain is 2 and your real function is in 3, it's not a 3-dimensional vector that you get, but it's a vector that's projected down onto the domain space. Okay, so with that, I'm sure that clears everything up perfectly, right? So let's just consider we're just going to walk through an example here, and this is pretty easy. So let's consider, now I changed this a couple times, going through trying to choose an appropriate picture for you so you can see everything nicely. So I hope I remembered the exact equation I have here. So let's see. I put z minus 2, so that should kick it up vertically 2 points or 2 units. And we have this. And we're only just, for argument's sake, to make sure we actually have a function here, let's just consider the upper half only. And then we can, HLAF, and then we're only considering the upper half of this. Now, to put this in function form, then, I'm going to solve for z. So we have z minus 2, And this is just going to be, oh, I'm sorry, this is a 25. See? I need that r squared right there. All right, so we have 25 minus x squared minus y squared, and then square rooting that. Now, of course, here I'd have to put a plus or minus, but I'm only considering the upper half, so I'm only putting the plus. So this entire thing is going to be above the x or above the xy plane, and by adding this 2, 1 here, it's just going to be the lowest z value is going to be a 2 then. And then to write it in the correct form, I need f of xy, and then I can find the gradient of that. And then to make sure I can find the gradient easily, I'm going to put this into exponential form, not radical form. So this would be to the 1/2, and then plus 2. That'll make it a little easier. Also, we are going to consider, let me see, a point on this. So what we're really trying to find here is the direction. So here's our goal. And I was just playing around with this formula, so that's why I didn't quite have this written out like how I should here. So our goal is find the direction of greatest increase at a specific point. P we have 0, 4, 5. All right, I just had to pause. I want to make sure that that point fit into there because I was playing around with this so much yesterday, actually, that I just want to make sure I have the right point. All right, so to get an idea of what's going on here, let's go over to GeoGebra. And I already put that in. So we have this upper half of a sphere right there. And notice that the smallest z value is 2, as indicated here. And the red axis is actually the x. So in this orientation, we have x. Come on, stop. Hello. X, y, and z. So we have a point, and hopefully if I did that right, it'll show up. 0, 4, 5. Okay, so there it is right here. So that point is on that sphere right there. Now, I chose this point 0, 4, 5 for a couple of reasons. One, the 4 and the 5 work out nicely, but the important part here is that I chose x to be 0. That way we can see this a little better, and you can also just see this if I make x 0 by looking straight down the x-axis. There it is right there. So now, if you look at this gradient then, let's come back over here. All right. Now, there would be a couple of ways we could do this. We could take this and bring everything over to the left and then make it a function of x, y, and z. For this one, I just have this function in x and y. And I think you'll see the gradient a little better here, and the direction of greatest increase a little better. So let's find the gradient of f. I think this is going to be fairly large here. All right, so the partial with respect to x then, so we have to bring this 1/2 down. And then all of this is going to go to the negative 1/2, which is going to shoot it into the denominator. All right, so we have 25 and that's to the 1/2 down there. And then the derivative of the inside is going to be negative 2x. Same thing is going to happen for the y. So all this stuff is going to go right here, of course. And then this is going to be minus 2y. And the half's going to be down there. Okay, so at the point 0, 4, 5, it's f of x and y. So we're going to just plug in the 0 and the 4. All right, so before we do anything here, notice that the 2's are going to cancel here, the 2's are going to cancel here. And then just ignoring this bottom for a second, we're going to get a vector. So this, just the top. So the bottom, I'm basically bringing down the bottom. So we have a 0 here, and we have the 4, which is right here. And then everything on the bottom is going to give us, so it's 25 minus x squared, which is 0, so that zeroes out. So y squared is 16, so 25 minus 16 is 9, and the square root of that is a 3. All right, so here, so we're talking about the direction. If we're talking about the direction only, I keep forgetting to put L's in there. If we're talking about the direction only, we have a vector of 0, 4 divided by some scalar 3, because that 3 is on the bottom, so who cares about that? So the direction is 0, 4. Now, if we really want to get worried about the direction, this is basically equivalent to a direction of 0, 1. Okay, we're really only worried about the direction, so if we look at that. All right, so if you remember from our picture here, now I will not be able to draw nicely on this because this is not within the program that we're doing. But if the direction vector is 0, 1, that, oh, wait a minute. That's not even right, is it? Because I forgot about, somebody should have been yelling, but if you were, I couldn't hear you. I forgot about this little negative right here, because right now, this doesn't make sense at all. I'll show you why, because this is actually negative. Negative, negative. Those little pesky little negative signs. And let me just actually draw it here. So I'm going to draw in from the side view, meaning I'm looking straight down the x-axis. So this is the y, and this is literally the z. So I cannot see the x-axis because it's just point on right there. So we have this 1, 2 right about here, and we're out here at a distance of 5, right? So I have something that looks like this. And our point is 0, 4. So 4 is about here. So that point is 0, 4, 5. And then look at our direction vector. Even though this thing up here is it's a three-dimensional object, so even this should look a little rounded, say, this little guy's coming around here, whatever, I can't draw. That the direction vector we got is a two-dimensional vector, 0, -1. So if we draw that in, and I'll do that in red, so from this vector from here. Now I'm just drawing it in reference to this because it really doesn't matter where I do this. The vector 0, 1, 0, -1, sorry, is in this direction. Okay, now I'm going to project this down to, so I'll get rid of that a little bit. Eventually here I'm going to project all of this figure down onto the xy plane. So if I bring this down, this vector here at the point 0, 4, which was our domain value, because down here is our domain in the xy plane, this actually projects down to here, or this vector is actually projected up to there. So that's the direction of greatest increase. Now you should be able to see that from here. If you, let's say that you were on this spot, and I can't draw on here. If you were in this spot right here, what direction would you go to increase? Well, you would actually head straight up this way. Well, it's not really straight. Why am I redefining that? I haven't seen that one. You would actually start traveling up the sphere in this direction. Okay, which means down on the xy plane from this point, you'd have to start traveling along here on your input values. If you travel along here on your input values, you're going to actually, this is your steepest ascent going up. Certainly if you head in some other direction, you're ascending, but not as steep as right here, and that shows us that that is our direction of steepest ascent, going up. And then, of course, what direction would be our steepest decrease is, so basically if you had a little ball right here, and this is where maybe the application here was, if you put a ball on this sphere, what direction would it start rolling? And the direction it would start rolling is the direction of greatest decrease. So it would roll right on down this sphere in this direction. And with some of these figures that are kind of wavy, like our sheet or our flag, our bowl, you know, our ball could start rolling really in any direction based on the steepest decrease. And as if the ball is traveling around, you'd have to keep following the steepest decrease on the way down. Generally, because with, you know, momentum and all that, it might not exactly follow that. All right, so what else did I want to draw here? Oh, that's what I want to draw. So let's pretend, and I'm not pretending, I'm just going to do it. So now I'm going to take this and project it down onto the xy plane. I hope this drawing is not too awful, and I'm just going to, I do not have a z here. It's only x and y. So here's my x, here's my y. And then what I'm going to project are called level curves. So a level curve, meaning if I take, let's say, a horizontal plane, let's say z is equal to 2. So a z is equal to 2 would come shooting right across here, which is a plane. Okay, that is a plane that shoots through there. And that would actually intersect this upper half of the sphere with a circle, and it would have a radius of 5. So this would basically come down here and here. Right, so this is basically projecting, this is supposed to be a circle. Sorry for that. And then let's say we have z is equal to 3. So if this is at 2, let's say we have 3, which is about here, say. Let me do these in red. So if this is 3, and then 4, and then this, say 5, I think what would the maximum be? 0, 0, 7. This goes up to 7, right? So this would actually go up to 7. So if you put out what's called these level curves, meaning the space between here and here and here and here and here and here, if you make them basically all the same and then project those down onto here, what you'll see is that this will be about here, say, and then say here, here. And then what you'll notice as you're creating these, and I did not do a very good job at this. So if you project that down and then this one, what you'll notice as you get toward the center is that you're going to have more space between the lines, and then right at the top you're going to have the dot. And what should have happened is that we have a very small space here and a greater space and a greater space and a greater space. I did not do a very good job here. And the reason that's true is because for the same amount of height here, you only have to go over a little bit. And then from here to here, notice if from here to here, we actually had to travel from like here to there. So that space should have been indicated a little bit better down here, and I just didn't do a good job here. And what you should see is that the tighter these lines are, now that should look like something if you ever see like a pressure chart for, like a weather system coming through. And if you see weather and you see these bars that are really close to each other, and then later, you see the bars spreading out. These bars that are really close show a great pressure change. The gradient of pressure change there is very great, meaning they're very close together. There's a lot of change from bar to bar, from bar to bar. Now the change is the same. So the change from here to here is the same as the change from there to there, because the change is this z distance basically. So that is the same. However, you're traveling over a shorter distance. So a short distance with a lot of change is a greater increase than a longer distance with the same amount of increase. I hope you understand what that's getting at. So if you see a weather system coming through and you see the little pressure bars are super close together, look out, you're about to get some weather. Because the pressure is going to change very quickly as it comes through. All right, now back to our direction vector. So that tells us then if we pick a color here. If we were right here, say at 0, 4, so the direction vector here is 0, -1. So that actually shows us that the vector is actually in the domain. You see that? Because that's what we're worried about. If we have some sort of thing going on here, the x and the y are the things that basically we control. We can travel around on here. The function tells us what's happening. So from here, we would like to know what direction we would have to travel to get the greatest increase, which would be in toward the middle, because then our pressure would go up, or would say this is pressure or something, whatever. It's going to go up. And then if we have this, so this is the gradient vector is in that direction, and then because that's the greatest increase, and then in the other direction, that's the negative of the gradient, and that's going to be our greatest decrease in that direction. All right, hope that clears things up. Let me just finish this up, and then we have to move on to a couple of other new things.